Good morning. It's always very nice to be back here. I have a wonderful sense of deja vu in that when I pulled up this talk to see what I was going to say as the background, I realized it was dated September the 20th, 2018, which would be roughly the day I gave it last year, which is tomorrow, I guess. I did modify it slightly. I am a professor of formerly of ecology, infectious diseases, and conservation biology. I started out as a zoologist looking at insects. I then started looking at parasites of fish as a research assistant, and then went to Oxford where I worked on the mathematics of bird populations and how they might be affected by climate variability. After that, I went back to work on diseases at Imperial College London, and then went to Princeton in October 1983, and I've pretty much been there ever since, working on all those different themes, essentially looking at, not necessarily in that order, infectious diseases, often of wildlife, but also of humans, problems in conservation biology, and fundamental problems in ecology. And while I'm here, I've realized eventually, sort of 35 years later, that the way to couple all those things together so as they're more broadly useful is to work with economists and look at how they affect human societies. And so that's the main theme of what I'll be working on here. What I'll walk through quickly today, that's just a sort of menu du jour, or it was the menu du jour of last year. The central core of what we're interested in very much appears in this video, if it works. This is the Amazon, and a group of people from Brazil came here in June, and I'll spend some of next week with them, looking at what's happening in the Amazon. And this essentially is concurrent. Go on, go for it, play the movie. Okay, it's not going to play the movie, which is a bit of a tragedy. But essentially what you would see starting out in about 1973, when I started my career, is a relatively intact Amazon. Through time, and through a sequence of photographs that NASA takes every year, you can see it being eroded and disappearing. And we know this summer it started disappearing more rapidly than it's been disappearing for the last 35 years. Now that plainly has consequences. It means that whatever lives in the Amazon has much greater difficulty living there or goes extinct. It also means that possibly the greatest source of carbon on the planet is put up into the atmosphere, which isn't a particularly good thing, but it also very sharply has consequences for the people who live there. So one of the central things we're interested in is, what is all this habitat conversion, which is very much the sort of theme of what's happened to the planet over the last 100 years. What are the main underlying patterns and drivers of that? How can we take simple models for that and build in risks of disease for humans, risks of diseases for their livestock, changes in the rates at which ecosystem services, cleaning the air, providing fresh water, how are those changed under land use change, and what are the consequences and interactions with climate change? And ultimately, what are the long-term economic and environmental costs of economic decisions that people make in the short term? You're worried, you want to raise money, chop down a bit of forest so as you can grow crops to feed your kids or send them to school or send them to Princeton. That's beneficial for you in the short term. What are the long-term costs of that for everybody else? And how can we develop a general mathematical framework that will provide insights into the Sustainable Development Goals? The goals that are supposed to guide the way we manage the planet over the rest of this century, if we have that long. Essentially, unless we get this sorted out by 2030, it is game over. Everything else you're studying will not be particularly useful because we will not have a viable planet to live on. Okay, so let's reduce this down to its simplest form. If we're making models of that, essentially what's going on is we have pristine habitat. We add humans to it who convert it to agriculture. It lasts as agriculture and then degrades, partly because you use up the soil, weeds come in. It becomes degraded land, which can, due due to the sort of forces of nature, colonization by the plants that were there originally, the insects and the animals, it can return to become pristine habitat again, which you can go and wreck again by converting it to agriculture. Sometimes we don't abandon agricultural land, we turn it into urban areas. And of course, you then have a tension that the urban areas have to be fed food that's supplied by the agricultural lands. And those agricultural lands are biologically sort of deserts, but they support humans, so the more attractive you can make them to humans, the more you can suck humans off the land so as they can live in urban areas and allow the land to either produce agriculture or produce ecosystem services, clean water, fresh air, etc. Now, interestingly, that's a process that has dynamics very similar to what I work on when I work on infectious diseases. If you think of something like measles, which should always be on your mind, particularly if you haven't had a measles vaccination, you have a population of susceptible individuals who are born. Someone coughs and splutters in them, or they touch something that hasn't been watched carefully. They get measles, they're infected. The older you get, the higher the chances of mass neuronal disease and dying. You may recover, mostly you recover, and then you're immune for life. You can move quickly people from the susceptible to the resistant class by vaccinating them with the world's safest vaccine. Now, very similar things are happening to land. Essentially, we have pristine land. We add humans as a sort of virus that convert it to agriculture. That agricultural land can be abandoned. It becomes abandoned land, which is resistant to further agriculture until it's been back through that process of being forest or restored. So you could move land from being pristine into nature reserves, which would be the equivalent of sort of recovered abandoned land. Now, the dynamics of that can be written down as 3 equations, into which we can add a 4th equation for humans. Those are very similar in form to the models we use for measles, and we can solve them all analytically. And essentially, it says, easily parameterized over the course of, say, 100 years, we have forest, which we add humans to. It converts the land to agricultural land, which degrades and becomes degraded land, and then you see the root of the problem. Only a very small proportion of the land ends up in agriculture, and we often have less land in agriculture than we had at peak agriculture, even though we've got a very large human population that's trying to support. And that is going to create stresses and tensions because people need to eat. In particularly places like France, you have to eat really well, and finding ways to manage land so people can eat and not get grumpy is often at the root of what we're doing. Disconcertingly, depending on how long agriculture lands, you end up with most land as degraded. So managing land is central to the global economy. We see echoes of that pattern in different pieces of data. This is the Philippines on the right. This is the west coast of the United States. Land is converted very dramatically from forest in the Philippines into agricultural land and eventually becomes degraded. In the US, the forest is knocked down in the west more slowly. Agricultural lands there, recovering land and urban land. So we see different patterns of that working at different speeds. And indeed, what causes it to work at different speeds, just twisted this round, what it settles down to is very much dependent on the length of time it lasts under agriculture. The longer you can keep it sustained under agriculture, the higher the proportion of the landscape will be agricultural land. The more rapidly it recovers from abandonment also reduces the amount of land that is in that unused state, but it's very hard to do anything that leaves you with any pristine land. And that's a worry. It should become a deeper and deeper worry. It's what Greta Thunberg's worried about. It's what I'm worried about, and it's what you should all be worried about. Particularly from the perspective of pathogens. So one of the things we've been asked about is what happens if we start putting pathogens into this framework, and what types of pathogens should we be interested in? So one way to think of this process from the pathogens perspective is you start off with complete forest and slowly convert it to completely agricultural or abandoned land. The types of things you should be worried about are what happens with pathogens that live in the forest that might come across and attack you as you develop agriculture. So the thing you're most worried about there is what is the perimeter of edge between the little patch of forest land when you start and the surrounding forest to the end when you have a little patch of forest and lots of agriculture. Plainly, the green line is the length of the edge, and the two lines are, one is the relative amount of pathogens living in the forest, the other one is the pathogens that might be living in the surrounding matrix. When you look at that, you can think, it's good to focus your mind on two types of diseases. One would be something like Ebola, quite a scary disease, but not something I worry a lot about because it has such unpleasant dynamics, it drives itself extinct quite quickly. You should be much more worried about measles than you should about Ebola. And then vector-borne diseases, which if you're here and being bitten by mosquitoes at night, that will also concentrate your mind because all of these, dengue, Zika, chikungunya, are all beginning to appear in southern France. So the rate at which those things are transmitted across that boundary peaks in both cases at that intermediate level of conversion. Obviously, once you've got rid of all the forest, there's nowhere for the bugs to come from, so they begin to disappear. Very early on, you have a very narrow perimeter, you're only a tiny area, so there's very little. So although it looks very fancy, it's actually pretty basic. What makes it slightly more interesting is you can calculate the size of the epidemic. And then just through time, as the proportion of habitat gets converted, goes from none through to all of it, you have this thing that you get relatively small epidemics to begin with. You then enter a period when you've either got small epidemics or massive ones. And you're always going to get them. So essentially, initial with about 10% converted, lots of small epidemics, maybe 1, 2, 10 people. Intermediate size, you're guaranteed epidemics. At the end, it's more bimodal. You either have very small ones or the occasional massive ones because you've got lots of people there to be infected by them. So if we look, going back to the Amazon, where as I said we have this collaboration, what's been happening there is this steady and progressive rates of loss of forest, conversion to agriculture. If we look at the different types of diseases there, here we see number of cases of the two different types of malaria, Plasmodium vivax and Plasmodium falciparum. As land use change converses, we're seeing more and more cases of malaria. If we look at dengue fever, similar thing, as land use progresses, more and more cases in more and more areas of dengue fever breaking out. So what other things change under land use? Getting sick should focus your mind, but there are other things that are important to you. Plainly, we start losing biodiversity. All the non-voting species on the planet, whose future we decide by our handful of votes if we bother to turn out. Those things supply ecosystem services, which are economic services supplied to the human economy, which are both tangible and, if you like, non-tangible. You know, they could be things like, wow, it's fantastic to go into that forest and see those monkeys. Wow, it's really nice to have clean water to drink every day. And you have that because of the way that the natural processes that operate in forests give you clean waters. All of those things will interact with climate change, because another consequence of burning that forest, driving around in cars, getting an airplane to go to New York, is you putting CO2 into the atmosphere, and that's steadily warming the planet. Ironically, the cheapest way to stop that is to stop chopping down forests and to speed up that process of land restoration, because that sucks carbon dioxide out of the air and puts it back in the soil. There are all sorts of other clever, fancy ways that people are thinking of doing it, but that's the cheapest way, and that's the one that creates the most jobs. Everything else costs us money and doesn't really scale up to the level at which we have to do it. So again, one way to think of this is, how are we losing biodiversity? Well, we know that as the land gets smaller, it can support less and less species. Big species, charismatic things such as tigers and leopards, require big areas, so they go extinct first. The things that I'm really excited about, bacteria and funguses and nematodes, you could have, there's a ton of that just around the base of that tree out there. Those go extinct much more slowly, and each of those different types of species are performing different tasks that are supplying different types of ecosystem services. So the really fancy things in red, the lions, the tigers, the leopards, they'll go extinct really quickly. We lose those quickly. We'll lose the aesthetics and they're being scared knowing they're out there. The deer and the wildebeest that eat plants will go more slowly. The plants will go relatively slowly because the biggest diversity is in the plants. The hugest diversity is actually in the fungi and the bacteria. They'll go extinct the slowest. So we won't have a steady loss of ecosystem services. We'll systematically lose things that are charismatic and aesthetic and go through to things that are fundamentally supplying things to us. Again, we could do a similar calculation to that risk of disease. At what level do we trade off the balance between good things we're getting from converting land and detrimental things we're getting from losing ecosystem services? And that's at some intermediate point, which will vary depending on the type of service we're interested in. So let's focus on one service, water. I don't worry a lot about water because I'm in France and I mainly drink wine and the odd beer, but if you really do need water for your shower, when I got here I didn't have a shower head, they miraculously found one, that meant I could have a shower and capitalise on the wonderful water that Marseille has. Now what if we were to put water into this framework? Because water plainly comes from rain, precipitation or snow up as you go further north. That is held for much longer periods of time in forested lands than it is on agricultural lands, where if it runs off too quickly, you get erosion. It causes chaos in cities, as you'll see in November, when we get all the showers we always get in November. Degraded lands, it always runs off, taking the soil with it. So to maintain water and supply it at a slow rate and to cleanse it, you need pristine habitats. You also need water for food. You can't have fresh salad and everything unless you have water to supply to agriculture. So we could again look through time, adding water into those equations. Just focus on the top to begin with. We have time, we have the same processes going on as before. Forests declining, biodiversity declining, agricultural land going up, degraded land going up. What is happening per square kilometre to agricultural productivity? Well, as you first open up the land, agricultural productivity per unit area will get bigger because the economies of scale kick in, you pests coming in from the forest are getting further and further away, so it will go up. But agricultural productivity is dependent on water, which is dependent on the amount of forest left, which may well, its cleanliness of that water may be dependent on the biodiversity measures there to clean it. So eventually you'll hit a point where suddenly you don't have enough water for agriculture, and your agriculture will collapse. Now we don't know where that point is, but we're doing the experiment on the global scale of messing around with land and water to find out when is our agriculture going to collapse. And that is going to, again, be bad news all around. There will be many political problems that we'll have to deal with. The additional tweak to that is that water is very much dependent on what the climate's doing. As are all of these processes, if climate change decreases, I've just put these in as dotted lines, the length of time that agricultural land lasts for. So instead of the solid red line, we'll have the dotted red line, because it's become degraded land more rapidly. That'll change the rate at which agriculture produces food. And climate change could push that in two directions. It could be that more water and warmer days makes agriculture more productive in the short term. It could be that more water floods the crops, or temperature's too hot for them, in which case agriculture will be less productive, and it also makes more fuzzy when this collapse appears. But your biggest break against that happening is to keep back on this half of the graph. Do not trash all that land and reduce the rate at which you get save water, because you want agriculture to stay safe and stable. You want human societies to stay safe and stable. We can then begin to put all of that together. Again, not making it too complicated, because we want to generalize this and we want to be able to take it to different areas and apply it, have these equations for land use change, add in human demography, and add in aspects of different types of pathogens. We can parameterize simple versions of this. And what we want to do over the next year, and hopefully the next 5 to 8 years if we get the grants that we're applied for, apply it to different regions. Look at how it affects the Mediterranean. Look at how it's already looking at how it affects the Amazon. Look at how it affects East and West Africa, and perhaps also somewhere in Central America. So when we start running these models forward, as always you discover even the simplest models suddenly have complex dynamics and can go into different directions. Depending on how well you do managing your water, how well you do managing your diseases, you can either have a healthy human population and a viable economy, or you can have pretty sick people and a crap economy. And finding out what switches you in each direction is the sort of ultimate goal of this project. So we've essentially been playing around with that. As always, it's very delightful to be here. I'm already been fascinated by some of the talks I've heard and look forward very much to talking with you. As it's me, I'm kind of peripatetic. I will disappear occasionally, but like a bad penny, as we say, I will keep coming back. And so it'll be delightful to talk to you when I'm here. I'm happy to talk, as I mentioned earlier, about elephants, wolves, tropical forests, FC Barcelona, and also cookery. And also Marseille. Okay, thank you.